Now let's think how random variables differ from the other. For example, what is the difference between these two? X is the height of the first person you meet when you go out to the street, and Y is the number of tails in 5 flippings of a coin. Obviously, there are many differences between these two, but I would say that the most important one is the set of possible values. So Y can take values 0, 1, 2, 3, 4, 5. It has 6 possible values, integer numbers from 0 to 5. And X can take any value in some range. And so it is impossible, for example, to meet a person with his or her height equal to 3 centimeters, for example, and it is impossible that for the number of tails in 5 flippings of a coin to be equal to, let's say, 182.5. So these two random variables differs in their sets of possible values. Let's consider another example. U is the number of people who will pass in 10 minutes under the window overlooking the courtyard, and V is the number of people who will pass in 10 minutes under the window overlooking the street. Here we see that sets of possible values for U and V are the same. So 0, 1, 2, 3, 4, 5, and so on. So integer numbers, or natural numbers to be more correct. Natural numbers and 0. But what is the main difference in this case? So set of possible values is the same for U and V. So I would say that as we know that there are much more people at the street, so it is more probable that number of people who will pass in 10 minutes at the street to be so this random variable V usually will take values more than U. So values of V, it is more probable that V will take a value more than the value of U. So the possible values are the same, but probabilities are different. So we can say that, for example, probability that U will take value, let's say 3, is 0.1, and probability that V will take value 3 is 0.01. So the main difference are probabilities. Not the values, not the possible values themselves, but probabilities to take this value. So for each value, we can say that this value is more often for U and more rare for V, for example, or vice versa. So to conclude, we can say that the main difference between random variables are a set of possible values, this is the first, and probabilities to take these values. So for each value, probability to take this value may be different for different random variables. And so this information in general, so what values and with what probabilities a random variable can take, this information is called the distribution law, or simply a distribution of a random variable. So when we say that we know the distribution of this random variable That means that we know what values with what probabilities it can take. When we say that these two random variables have the same distribution, have equal distributions, that means that they can take the same values with the same probabilities. But the next question is how to describe a distribution, how to describe a distribution law of a random variable. There are three ways to do this. The first way is valid only for discrete random variables, and sometimes we call this a distribution table, sometimes we say we're using term PMF. So for a discrete random variable, as its set of its possible values is a set of isolated points on the numerical axis, we just can draw the table and fill this table with all possible values of a random variable, and for each value we can provide probability to take this value. And so in this table, xi is a possible value of the random variable, and p of xi is probability that this random variable will take this value, will take value xi. Sometimes this function that returns that for every possible value of a random variable that returns probability to take this value, a function of this kind is called a probability mass function, or PMF. You should know that it depends on a textbook you are using. For some textbooks prefer using this term, using this concept of PMF, and so they usually say what is the value of PMF in this point, for example, and some textbooks prefer to avoid this term, and they say just distribution table or distribution law or probability to take a certain value. So sometimes this term PMF is avoided. So it depends on the book you're using. Okay, and what is about continuous random variables? How about them? Obviously, it is impossible to fill such a table for a continuous random variable. Why? Because as a continuous random variable can take any value from some range, it is impossible to take all these values and to fill the table with these values, because when you take any pair of values, there is an infinite number of missed values between them. So this way that is valid for discrete random variables is obviously not valid for continuous ones. So for continuous random variables, the main way to describe its distribution, to define its distribution, is a function that is called PDF, probability density function. So this is a function that can look like this figure you see now, and looking at the plot of this function, you can understand which values are more often for this random variable and which values are less often, more rare, and which values are impossible for it. So you see that values that correspond to the high values of the PDF are more often values. Values that correspond to the arguments that correspond to the little values of the PDF are more rare, are less often. And so if you see that the PDF is equal to 0, this means that these values are totally impossible for this random variable. It never takes such a value. So it is usually enough just to have a look at the plot of the PDF of the random variable to understand which values are more often and which are less often, which are more probable in our terms, in the terms of our science, and which are less probable. So, but how about mathematical definition? So I say more probable, less probable, but how about the probability? How can we find the probability that a random variable of our interest will take a value in certain range, for example? So I have some interval of interest from A to B, and I'm interested in probability that the random variable x will take value from A to B, value that belongs to this interval. So this value is equal to an area between the plot of the PDF and the x-axis. This area in calculus, from calculus we know that this area is an integral. So this area is equal to an integral from A to B of our function. So, and this can be used as a mathematical definition of the PDF. So the definition is that a probability density function of a continuous random variable is such a function that probability that x will take some value from A to B is equal to an integral from A to B of f of the PDF. So using this definition, we can prove that integral from minus infinity to plus infinity of any PDF is equal to 1, because any random variable with probability 1 will take some numerical value, will take a value from minus infinity to plus infinity. That is why this is the main property of the PDF. So integral from minus infinity to plus infinity of any PDF, of any random variable, is equal to 1. We will use this property while solving examples. So, but is there a common way to describe a distribution for discrete, common for discrete and continuous random variables? Yes, there is. And it is called CDF, a cumulative distribution function. Sometimes in some textbooks they prefer term distribution function, so without this word cumulative, but the more general term is CDF, cumulative distribution function. So it is defined as you see. So they usually use capital letter F to denote this function, and in each point, small x, this function is equal to probability that capital X will take value less or equal than small x. Be careful here, capital X and small x are two different entities. So capital X is a random variable and small x is a possible value of this random variable. So in each point, in every point, CDF is equal to probability that a random variable of our interest will take value less or equal than this point. So left of this point if we look at the numerical axis. So what are the properties of the CDF that are direct consequences of this definition? So as we see that CDF is a probability. So right of the equality in this definition we see a probability P of capital X less or equal than small x. So, and as a probability is a number from 0 to 1, that is why so we see that this function can take only values from 0 to 1. So the plot of this function lies in this range between 0 and 1. So if we substitute plus infinity for x, for small x, so what is f of plus infinity? So this is probability that our random variable will take value less or equal than plus infinity. This probability is obviously equal to 1 because all numbers are less or equal than plus infinity. So in plus infinity, CDF of any random variable is equal to 1. If we substitute minus infinity, so this is probability for capital X to take a value less or equal than minus infinity. That is impossible because all numbers are more than minus infinity. And so this probability is 0. So limits of any CDF when its argument tends to plus infinity and to minus infinity are 1 and 0 respectively. So, and how this function behaves between 0 on the left and 1 on the right. So let's imagine that, let's say that x is the height of the first person I will meet at the street. So, and let's consider two probabilities. Probability to meet a person with its height less than 160 centimeters, and probability to meet a person with his height less than 170 centimeters. So, you see that if somebody's height is less than 160, it is automatically less than 170. So this event, that height of the first person we will meet is less than 160 centimeters, is a subset of the second event, that his height will be less than 170 centimeters. So, and because of these, we can say that probability to meet a person with his height less than 160 is less or equal than probability to meet a person with his height less than 170. So this means that when the argument of our function of the CDF is increasing, its value is also increasing. So the plot of the CDF looks like this. This function cannot decrease. It can either increase or stay constant, but it cannot decrease. So these properties are just direct consequences of the definition of what the CDF is. And let's now describe them with formulas. So the first property is that the value of any CDF is between 0 and 1. The second, its limit in minus infinity is 0. The third, its limit in plus infinity is 1. The fourth, if x1 is less than x2, then f of x1 is less or equal than f of x2. So this means that this is a non-decreasing function. And the fifth one is that for any random variable, probability to take value from some range, from x1 to x2, is the difference of values of its CDF in these 2 points. So if we subtract probability to take value less than x1 from the probability to take value less than x2, what is left? Probability to take value between x1 and x2 is left. So this is the fifth main property of the CDF. So we know that the distribution law of a random variable can be described with the help of the PMF or CDF if it is a discrete random variable. So that means there is some kind of a relationship between them. So when we have got a CDF, we can obtain the PMF and vice versa. So how this can be done? You can see this on the picture. So if we have a table with all possible values of the random variable of our interest, let's say that there are 4 possible values, x1, x2, x3, x4. And if we know probabilities, so 4 probabilities for each of these values, the CDF of this random variable looks like stairs. So it is equal to 0 left of x1, it is equal to 1 right of the x4, and in these 4 points we see stairs, and height of each stair is equal to the respective probability. So height of the first stair is P1, of the second one P2, of the third one P3, of the fourth one P4. So that is how we can get a CDF when we have the PMF and vice versa. As for continuous random variables, everything is very simple. So the PDF is a derivative of the CDF, and the CDF in its turn is an integral of the PDF, as you can see. So it is very easy to get a PDF when you have the CDF, and a little bit more difficult to do the opposite operation, but still usually it is possible. So that is how the distribution of a random variable can be described, and that is how we can establish a relationship between these different ways to describe a distribution. So let me show you an example how we can describe a distribution of a discrete random variable. So let's say that there is a box and there are 10 white and let's say 2 black balls here, and I choose 3 balls at random, and I am interested in the number of black balls in these 3 I have chosen. So let x be the number of black balls in those 3 chosen. So what values this random variable can take? Obviously 0 or 1 or 2. So as I have only 2 black balls, there are no more than 2 in these 3. So how this distribution table will look like? So here I have possible values 0, 1, and 2, and here I have probabilities. And so to to describe a distribution, to define the distribution of this random variable, I am to find these three probabilities. So we have already solved examples of this kind. So here I need to use discrete uniform probability law and the number of combinations. So what is Px of 0, or probability that capital X is 0? So this is probability that all three balls chosen are white ones. So the experiment is choosing 3 out of 12. So number of all possible outcomes of this experiment is 12, choose 3. And favorable outcomes are such outcomes that there are no black balls, so that all three are white, so all three are chosen from these 10 balls. So number of favorable outcomes is 10, choose 3. So now let's count. Here I have 10 factorial divided by 3 factorial times 7 factorial. And here I have 12 factorial divided by 3 factorial times 9 factorial. So 3 factorial is cancelled, and here I have 10 factorial times 9 factorial, and here 7 factorial times 12 factorial. So now I can say that 9 factorial is 7 factorial times 8 times 9, and 12 factorial is 10 factorial times 11 times 12. So this is cancelled, and this is also cancelled. And so what is left? 8 times 9, 11 times 12. Or, if we simplify this fraction, it will be 6 over 11. So, I have got the first probability, 6 over 11. Then, the second one can be found in a similar manner. So Px of 1, or probability that x is 1. So this, in this case, denominator is the same, as we have the same experiment. So 12, choose 3. And here in numerator, I have I need one of these 3 balls to be black and 2 others to be white. So 2, choose 1 times 10, choose 2. 1 is chosen out of 2 blacks and 2 are chosen out of 10 white. So 2 choose 1 is just 2. So this is number of ways to choose 1 out of 2. There are 2 ways to do so. So this is simply 2. What we have here? Here we have 10 factorial divided by 2 factorial times 8 factorial. And here we have 12 factorial divided by 3 factorial times 9 factorial. Okay, as 2 factorial is simply 2, so this is cancelled. And what is left? 10 factorial times 3 factorial times 9 factorial divided by 8 factorial times 12 factorial. And after simplification, this is 9 over 22. So this is the second probability. And after these two have already been found, we don't need to calculate the third one in a similar manner, because the sum of these three probabilities is to be equal to 1. So that is why this one is just 1 minus this minus this. So it is 1 minus 7 over 11, or I can say 12 over 22 minus 9 over 22. That is 22 minus 12 is 10, and minus 9 is 1. So 1 over 22. This is the probability of the third value. So now we can plot the CDF of our random variable. After we have got the table, after we know its possible values and their probabilities, so we can plot a CDF. So, as I have three possible values, the CDF has 3 stairs. So, 0, 1, and 2. Height of each stair is equal to the respective probability. So, here, left of 0, my function is equal to 0. Here, in 0, I have a stair, and its height is 6 over 11. It's almost 1/2. So, this is 6 over 11. And the value of the function does not change between 0 and 1. And in the next point, here in 1, I have another stair, and its height is 9 over 22. So the value of the function here is 6 over 11 plus 9 over 22. That is 21 over 22. Between 1 and 2, the function is constant. And here it has the third stair, and its height is 1/22. So the value of the function is 1. And so this is how the CDF looks like in this case. So the height of each stair is equal to the probability of this value.